Okay, so those were the loose ends. I've encouraged you before to make sure that you read this stuff in the book, because I'm not talking about absolutely everything in there, but those were the loose ends that were in that section of the book. Okay, let's look at the work energy problem. Why don't we play with this one? Happens to be number 132. We have a pendulum, and you did pendulum problems previously in physics, and this one swings down. It's on a 1.2 meter arm, massless arm for the physicist in here. Okay, we're going to neglect the mass of that. We're going to treat the body A. They don't even tell us what the mass is, but we're going to treat that as a particle. And let's see what's going on here. In the position shown, at 60 degrees from the vertical, it happens to be noted that it has a velocity of 3 meters per second at that instant, and is swinging in a vertical plane. At the bottom of the position, as the thing is then straight down, there's a pin here at B, and then that mass is going to come whipping around on a tighter radius now and swings up. And the question is, calculate the velocity of the ball as it passes position C. Position C is horizontal to where that pin is. We want to figure out the velocity when it gets to C. So the body is on this arm, initially at 60 degrees. Here's the mass, mg, sweeps down in a circular path until it gets down here. See, I think the body was A, this pin was B, horizontally from pin B is, and then this thing's now going to swing on a tighter radius to location C. And the question being asked is, what's the velocity or the speed at C? They also give us a little more geometry. Happens to be 1.2 and 0.8 meters. 1.2 meters here and 0.8 meters from the support point down to B. Anybody here a yo-yo buff? No? I should have brought my yo-yo in. Ever since I was in junior high, you used to play with yo-yos. So they used to have contests. The Duncan yo-yo representative would come down to, usually near a drugstore out in the parking lot, and they'd have all us kids get down there, and we'd start doing our yo-yo tricks, and then if we won, we would get a free yo-yo. Well, one of the moves you'd do is you'd throw your yo-yo out, and so it's just like a pendulum like this. It comes swinging around, and then you hold your finger out here, and that yo-yo string comes up here, grabs that, and then the yo-yo flips over just like you see in this problem, and comes back and lands on your string over here, and then you flip it back the other way and bring it back and catch it in your hand. Can't remember what that one was called. Another one was Round the World, where you just get it out there, it sleeps, and you let it go around a few times, and then you snap it back to your hand. So I'll see if I can dig out an old yo-yo out of the box someday and bring it in. 'Cause that's dynamics, you guys. Okay. Okay. So we have a 1.2 meter arm starting out at 60 degrees, and I don't like my picture. Why not?
Because A is going to be above the line.
Yeah, I like drawing somewhat to scale. So Let me just change this angle. Make that more like 60 degrees. That feels better to me. Is that right?
Yeah.
Is that a good free body diagram? Before we start writing equations?
No, we need attention.
Thank you. So what we like to do is treat our particle as a free body. That's what free stands for. Okay? So you pop it loose, and so there's going to be, because of the dynamic, because of the motion, there's going to be tension in that cord. That tension, by equilibrium compatibility, then carries back up onto this segment of the cord, and it's pulling clearly on that pin up here at the top. Okay. So now we have a better free body. Feel good about that. Okay. So we could do this thing with F equals ma. But let's try playing with U equals change in kinetic energy. The work done by the active forces is equal to the change in the kinetic energy. Okay. I'm going to label this point down here at the bottom. Do they have that labeled on the problem? No. No? Let's call that D. Okay. Let's call that D. Because I'd like to do more than just answer the question, what the velocity is when it gets to here. Okay. Let's start by answering the question, and then we can go back and play with other interesting features. So, we want the work done in the particle moving from this position, we'll call it 1, to this position called 2. The work done by the active forces. What are the active forces? What forces do work?
mg.
mg. What about T?
That'll never work as in direction. It's never in the direction of the
It's never in the direction of the displacement, is it? No. That force always remains perpendicular to the motion, even after it gets on here. Okay? So T does not do any work. mg, however, does. So we better look at the geometry here a little bit, because we need force, mg, times some distance traveled. mg times some distance traveled. And so let's figure out what that distance is in moving from position 1 to position 2. So I think another little geometry sketch might be useful. So if we have this as 60 degrees, then the vertical motion for it to reach this level where B and C sit is going to be 1.2 cosine 60. So this is 1.2 cosine 60 is the, I'm sorry, that's actually not where BC sits, that's where A is, isn't it? Isn't that the level at which A is at?
Yeah.
Yeah, that's the level at which A is at. Right? And so that's the same as sine of 30, which is a half. So this distance is equal to 0.6. 0.6. Now, B and C are at a distance of 0.8 meters from the support point. 0.8 meters from the support point. So that happens to be down here. B and C are down here at 0.8 meters from up above. So what's happened is that mass, mg, that weight, mg, has moved physically downward 0.2 meters in the same direction as mg. So the work done by mg in this motion is 0.2, is whatever mg is, value-wise, times 0.2. Motion downward. Is that all right with people? Okay. So what we have here then is we have mg times positive 0.2. That's equal to the change in kinetic energy. The change in kinetic energy is equal to 1/2 the mass of the particle times the speed it has at location 2 minus the energy of its motion, 1/2 mv squared at position 1, the speed it's carrying at position 1. So substituting in then, this becomes equal to 1/2 mass gets factored out. V2 happens to be here at location C minus V1 happens to be the speed it was carrying initially, which they tell us in the problem was 3 meters per second. So I'll put that here. V sub A is 3 meters per second. So here's our equation. So you notice that the mass divides out. This problem then is independent of the mass of the particle. And we then solve for Vc. So the velocity of C then is going to be equal to 2 times 0.2 is 0.4. G is 9.81. Kick this over to this side. And I have to add to it 9 by bringing the negative 9 over. And I need the square root of that to find this value. I'd like to see if you folks can punch things faster than I can, which you probably can because I don't have my glasses on. 3.59.
Yep.
So we get 3.59 meters per second.
Is it velocity at C or D?
We know the angular velocity. If you've done this, you see the angular velocity increases a lot. But that's just because we have a shorter radius. But if it's moving at the same speed, that's interesting.
Well, you know that force is a conservative field. And it's just a state function independent of path. So
Exactly. Yeah. You want to? Why don't you say that again a little bit louder so everybody hears you? What you said.
gravity is a conservative force field, and so any movement in that is a state function. So you only need to look at your initial position versus your final position.
That's right.
Take a difference.
And we'll clarify that mathematically next week with you. Okay? It's independent of the path.
So that means that it would have been going 3 meters per second if it had gone all the way back up. Let's say point C was.
Well, it can even be on this short radius here. When it gets back up 0.2 of a meter higher than this level right here, when it comes whipping around and it's right up here at the same level it was initially, its speed will be angled that direction, but it will still be 3 meters per second. Because think about the physics of this motion. It had 3 meters a second when it started out here. It gives up stored gravitational, I'll go ahead and start using the word potential energy. There's stored energy in there because it's up higher than where it goes. It gives that stored energy of that elevation up and transfers that stored energy into energy of motion, kinetic energy. So when it gets down here at the bottom, it is fastest in that pendulum's motion. It's moving fastest right down here. And then, as it starts coming back up, it is storing energy back into gravitational, it's storing potential energy back in because of it's giving up that mg effect as it rises back up. It takes energy to do that, to rise up against gravity. So it's storing that potential, and then it's giving up some of that speed. And it gets back up here, it's only 3.59. Now, the point someone made a moment ago is this is just like me playing with a yo-yo, and I knew this as a kid without the mathematics, is this is on a much shorter radial arm. Happens to be just a 2/10 of a meter radial arm, right? So if we take a second to look at that, this is a 2/10 radial arm. So what we have going on right there is the particle is in this path on 2/10 radial arm, moving vertically at that instant at 3.59, but that 3.59 is equal to r times omega in this circular path. So 3.59 has to equal this 0.2 radial arm times the omega, the angular speed it happens to have when it's on this short radius. And so that's going to be 5 times, this is 1/5, so the omega reading there is going to be 5 times the 3.59, and that's roughly 17 and a half or so. Huh? What was that?
Wouldn't it be a 0.4 radial arm?
Well, I'm sorry, did I mismark that? Let's see, this is 0.8 overall. Hold it. No, this is 0.8 to here. Oh, 1.2. Yeah, I miswrote this. This is 4/10 radial arm. Now, did I screw up the...
So what was the point of the triangle then?
Okay, oh, this distance right here was 0.2,
Right.
right?
Yeah.
That distance is 0.2, which was the work done, the distance traveled by that mg force downward to get to here.
And that
Oh,
arm's also,
same function.
that 0.4 arm is also going to be 0.2. It's just coincidentally the same thing. 0.2 down from the
Yeah.
ball position to the pin,
Yeah.
and then another 0.2 down to the
And so this
bottom of the arm.
this arm here is 0.4, and that's 0.4, and that's 4/10, which is 2/5. So this is I'll just write it as divided by 0.4, and if you punch that, what do you get? Roughly 9. You get 9 radians per second. 9 radians per second. Okay? I want to stick with this problem for a little bit longer because what I would like us to do is to see if we could generalize this. Here's an initial velocity that we happen to have, and let's say we put this thing at some initial angle and then just see if we can come up with a formula that describes the speed this thing happens to have at any point in that pendulum swing. At any point in that pendulum swing. So that should be pretty easy to do.